When we're dealing with independent events, our probability formula that looks like probability of A and B equals probability of A given B times probability of B just becomes the probability of A times the probability of B, because when they are independent, the probability of A given B is just the probability of A. Okay, so this rule here in the bottom of your screen holds for independent events. If our events are not independent, we need to make sure we have the probability of A given B. Let's look at some examples. Suppose that 49% of babies born in the U.S. are girls. Let's find the probability that 3 randomly selected births are all girls. Okay, so we're looking for the probability that our first is a girl, then our second is a girl, and our third is a girl. But each of those are independent. If I choose a baby at random and then choose another baby, whether or not that second baby is a girl is not dependent on whether the first was a girl. Okay, so we can recognize that these are independent events, and so the probability that we're looking for can be found by just multiplying the probability of drawing a girl on each draw. So the probability that we get a girl on the first draw is 0.49, since 49% of babies born are girls. And then the probability of getting a girl on the second draw is also 0.49, and same for the third draw. So our total probability is going to be 0.49 times 0.49 times 0.49. So if you plug this into your calculator, you get 0.118 if I round. Let's look at another example. According to a Wall Street Journal survey, 70% of consumers prefer to shop online rather than in person at their favorite retailer. Suppose 3 consumers are randomly selected with replacement from the population of consumers. Let's find the following probabilities. So we want to know the probability that all 3 prefer to shop online, none prefer to shop online, and at least 1 prefers to shop online. We're going to start with all 3. So these are independent events because one consumer's answer is not going to affect the probability of the second or third consumer's answer. So the probability that all 3 prefer to shop online is the probability that the first prefers to shop online, and the second prefers to shop online, and the third prefers to shop online. Since these are independent, I can just multiply the probabilities on each draw that I get someone that prefers to shop online. According to our information, that's 0.7, right? 70% prefer to shop online. That's a shocking amount. So 0.7 times 0.7 times 0.7. Again, you're going to plug that into your calculator, and you get 0.343. So the probability that all 3 prefer to shop online is 0.343. What about the probability that none of them prefer to shop online? So to do this one, we first need to know what's the probability that a chosen customer does not prefer to shop online. Well, not preferring to shop online is the complement of preferring online shopping. So we can find that probability by taking 1 minus the probability that they prefer to shop online. So 1 minus 0.7 or 0.3 is the probability that a randomly chosen consumer does not prefer online shopping. All right, so our second problem was the probability that none prefer online shopping. That means that all 3 do not prefer online shopping. Again, when we choose a customer at random, whether or not that customer prefers online shopping is not dependent on knowing about the other customers. So those are independent events, and so I'm allowed to multiply those probabilities. So the probability the first does not prefer online times the probability that the second, I'm going to say not online just to save some writing, and the probability that the third does not like shopping online. Now in each case, we saw that the probability of choosing a customer or a consumer that does not prefer to shop online is 0.30. So I'm going to multiply 0.30 3 times. So 0.30 times 0.30 times 0.30 is 0.027. Now let's look at the third part. The third part wants to know, what's the probability that at least one prefers online shopping? Now the at least one can be tricky to compute, because if at least one prefers online, it could be that one of the chosen consumers prefers online, or 2 prefer online, or 3 prefer online. Moreover, if we have one that prefers online shopping, is it the first one, or the second one, or the third one? This becomes really difficult to compute. So instead, what we want to do is think about this in terms of the complement. So what does it mean if I say not at least one prefers online? Let me correct my spelling here. Well, if not at least one prefers online, that means that no one prefers online. So not at least one always means none. So this says none prefers online. But we found the probability of that, right? We saw that the probability that none prefers online on the last slide, let's double check what that was 0.027. Okay, well this is the complement of the probability that we are looking for. So if I want to know the probability that at least one I can take 1 minus the probability that none prefers online. That's just my complement rule. And now I'm going to do 1 minus 0.027. Which gives me 0.973. Okay? So anytime you see at least one, you should ask yourself, would it be easier for me to compute the probability that none does whatever you're looking at, and then take 1 minus that to find the probability that I'm asked for. Okay, so at least one is always an indication to think about the complement. Let's look at another example. This is genders of babies again. So given 49% of babies born in the U.S. are girls, let's find the probability that among 3 randomly selected births, there is at least 1 girl. So again, what I'm looking for is a probability for at least 1. At least 1 girl. Now, if I wanted to find that probability directly, I'd have to think about how many ways I could have 1 girl or 2 girls or 3 girls, and then which of the girls which of the babies are the 1 girl or the 2 girl. And again, that's really complicated. So let's not think about it that way. Let's think about the complement. So the complement of at least 1 girl, so not at least 1 girl, just means no girls. So let's think about that probability. What's the probability that we get no girls? Well, that means that all 3 of the babies chosen are boys, right? So we could write that as the first is a boy, the second is a boy, and the third is a boy. I'm going to save some writing, write it like this. BBB for boy, boy, boy. Okay, so that we choose boy, boy, boy. Now on each random selection of a birth, it doesn't matter what happened previously, so these are independent. So this probability is the same as the probability of getting a boy times the probability of getting a boy times the probability of getting a boy. What is the probability of getting a boy? Well, the probability of getting a boy is 1 minus the probability of getting a girl, since it's the complement of choosing a girl. So 1 minus 0.49 or 0.51. So I'm going to multiply here 0.51 times 0.51 times 0.51. That's going to give you, let's plug it into the calculator, 0. I'm going to write it all out. 132,651. So that's the probability of selecting 3 boys or no girls. And so the probability of getting at least 1 girl is 1 minus the probability of getting no girls. So I'm going to take 1 minus 0.132651. Which gives me 0.867349, or if I want to round, 0.867. Okay, so the probability of having at least 1 girl when we choose 3 randomly selected births is 0.867.